Welcome to this video. In this video, I'm going to be talking about some techniques that can allow us to look inside the brain of a large language model. Because if you are able to perform an equivalent of a brain MRI on an LLM, we would be able to answer some interesting questions, such as, is the amazingly good performance of ChatGPT or GPT-4 a result of memorization that is based on surface level statistics, or are these models truly building an understanding of the world around them based on the data that they've been trained on? There's a lot of debate about, can we trust the content that is coming out of large language models? And here's a story from New York Times where they quoted a University of Washington linguistics professor, Emily Bender, who talked about language models as being stochastic parrots. She talked about LLMs as software that use randomization to merely remix human-authored sentences. So you can go look at this story yourself. Irrespective of how you feel about what language models are doing and whether you can trust the content or not, it is very clear that genuine progress in this field of large language model depends around notions such as meaning and understanding. And I'm not going to get into the philosophy of these notions. I have a link to a very interesting paper that I encourage you to go ahead and read. I think anybody who's used ChatGPT or GPT-4 will probably agree that these models are doing a little bit more than just surface level statistics. In fact, let me give you an example that I first heard in a Fireside chat between Ilya, Sutskever, co-founder of OpenAI, and Jensen, Huang, CEO of NVIDIA. Here's the example that Ilya provided. Imagine you're reading a detective novel. That novel involves a complex plot that's unfolding. It involves multiple characters and a series of events. And throughout this book, through the mysteries, through the clues that are presented, but the resolution is still unclear. And at the climax of this book, the detective gathers all of the involved parties and says the following thing. I'm about to unmask the individual responsible for the crime, and the name of that person is. The detective is expected to predict that name. And what's fascinating about this example is that if this was GPT-4, the chances are that it would get that name right. So clearly it's doing more than just surface level statistics. It is understanding the entire plot, the mysteries, the unfolding events. Let us return to the topic of this video, which is about brain MRI and LLM. The idea is to understand what is happening inside a large language model. This is when we go to this influential paper that just came out a few months back called the Emergent World Representation. The authors of this paper are really talking about how large language models can develop a world representation around the data that they've been trained on beyond just surface level statistics. A link to this paper is provided at the bottom of the slide. I encourage you to go download this paper. The rest of the video starting now is going to focus on some important findings from this paper. The authors of this paper decided to create a large language model, but a constrained one so that they could study it better. Always a good engineering principle. If you have a large problem, if you have billions of parameters, as you have in GPT-4, it's hard to understand what is going on. Can we create a simpler model, a constrained model, and then try to understand what is happening under the covers? The authors of the paper decided to create a language model that was trained on a game script of a game named Othello. You may know this game as Reversi. And the idea is simple. You have an 8x8 board with 4 discs, 2 white and 2 black, placed at the center. Black always moves first. Every move must flip one or more opponent discs by outflanking. By that I mean by sandwiching the opponent discs. The opponent will then repeat the process, and the game ends when there are no more legal moves. I'm going to show you a very quick example. I'm going to go ahead and make the first move. I'm going to select this location, and this will cause the center disk to turn black. And looks like the white made a move also. I can come in and select this location, and then on and on. The game will come to an end when there are no more legal moves to make. The game sequence, every such move that I am making and my opponent is making, think of it as a sequence that we are going to train the large language model on. So let's go ahead and take a look at the parameters of this language model being referred to as Othello-GPT. So here you can see in GPT-4 or GPT-3, we are using an English vocabulary of something around 50,000 words, versus we have a vocabulary of 60 words. So it's an 8x8 board game, 64 possible moves. 4 of those locations are reserved because that's the starting point. So we have 60 words. In case of GPT-3, we have 96 layers. And here, the authors of the paper created a transformer model which is 8 layers deep. In terms of the dimensional space, GPT-3 has 96 by 128, 12K dimensional space versus Othello-GPT dimensional space is 512. And finally, each game script is about 1K. So it's been trained on 100,000 games versus, of course, GPT-3 was trained on 45 terabytes of text. So as you can see, we've created a constrained language model, which is going to help us understand what is happening under the covers. Let us look at some additional details associated with Othello-GPT. First and foremost, it is important to remember that the model has no understanding of the game or its rules. All the model is seeing is a series of tokens that represent the moves made by the two players, and it is trying to develop an understanding. So if we started out with this untrained model, as you would expect, it has a high error rate. And then we start training the model. Where did we get the training data from? Well, it turns out that you can download the game sequences from the Othello Championship website. So that was what was used to train Othello-GPT. In addition, the authors of the paper created a large synthetic data set. And the way they created the synthetic data set was they took a game tree and generated legal permutations and combinations based on a game tree. So in this manner, they generated both data from the championship website and also synthetic data. And what they found was they were able to reduce the error rate to 0.01%, which means after having seen these moves, the model starts to play this game and has an error rate of 0.01%. At this point, you're thinking to yourself, is the low error rate 0.01%? Is it because the model has somehow memorized all of the legal moves? That's how we are getting this low error rate. To counter this argument, in this paper what they did was they took all of the 4 legal positions that initiate the game. So here are the 4 positions. And what they did was they took out one of the 4 initial moves and constrained the model to play in a manner with one less move. And think about it. This really means that there is 25% less moves available for the model to play this game. As a result, it will be forced into a game sequence that it has not seen before. Even with this one constraint of removing one initial game move, the model achieved an accuracy of 0.02%. So the error rate of 0.02% is good, but you may still not be convinced. After all, we are using an 8-layer transformer. It ought to be able to handle the additional complexity that we are throwing at it by removing 25% of the game moves. So at this point, let us explore the paper further. Let's talk about something called the probe classifiers. And this is an established technique within the deep learning community that can help you test an internal representation of information inside a neural network. And think of a probe as a mini neural network itself. And the authors of this paper decided to use a two-layer network as a probe for understanding Othello-GPT. Now, I realize that I'm using some of the terms that you may not be familiar with. So I'd like to point out a blog post here. And here's a blog post that I authored a few years back to provide basics of deep learning, but from a perspective of a developer. And in this blog post, I talk about a common problem of recognizing handwritten digits. And I go through the various concepts. And if you go through this rather long blog post, you will see at the end of this code associated with this deep neural network. Let's use this diagram to make a few points about the concepts that are relevant to the probe. So if you know nothing about deep neural networks, one thing you should understand is it has multiple layers, hence the name deep. Each layer has weights associated with that. So as we train a neural network, we are adjusting the weights in the hope of reducing the error rate, as we did with Othello-GPT. So we brought the error rate down to 0.01%. Once you've reached the optimal error rate, at that point you have the weights at various layers. Our job with the probe classifier using this mini neural network is to go to a certain layer in our neural network and try to understand what did it learn. So let me bring up this diagram right here. So this is from a paper that talks a lot more about probes, and the link is provided at the bottom of the paper. The key thing to take away from this slide is at the top of this slide is the deep neural network that is designed to recognize handwritten digits. As you can see, there are multiple layers here. At the top, we injected the probe at certain layers. And what you're seeing at the center of the slide is the drop in error rate associated with each layer in the network. So as you can see, there's a big drop off at the point where the ReLU layer was injected. And once again, you can look at my blog post. I talk about a basic understanding of ReLU layers and the various layers involved here. And you can see each layer, the error rate goes down, which means our model is learning some new concept. Now that we understand the notion of probe classifiers and how they apply to our model, let us take a look at how the authors of the paper utilized these probes within the context of an understanding of Othello-GPT. So they trained the probes to predict the internal state of the board. Now keep in mind, we never told the model about the rules of the game. All we did was we passed along game sequences. And we are trying to understand if the model recreated an understanding of the board. Does it have a representation of the current state of the board? And the way we are doing that is by applying probe classifiers at different layers and trying to see if it can predict the board state. And the results are interesting. We find that if you look at the accuracy of the probe classifiers at different layers, you can see that the error rate is going down. So we can say that the model does indeed have a valid representation of the board state. At this point, we have some evidence that our model has developed an internal representation of our board state. But maybe you are still not convinced and you're looking for some additional evidence. So we go to the next concept in this paper, where we try to artificially intervene an ongoing game and see if our model has developed enough understanding of the rules of the game to adjust to the changing situation. So for example, we went to the cell E6. Right now it has a black disk. And we are going to artificially intervene and convert this black disk into a white disk. And here the experiment really is that we are artificially intervening, changing the color of the disk. And if our model has learned enough about the rules of the game, it should be able to adjust to this change that has happened underneath the covers. Before we answer the question about what was the effect of the intervention that we just made, let's just take a moment to answer this question that may be in your minds about how did we change the white disk to a black disk artificially. And once again, if you go back to the blog post that I talked about just a moment ago about deep neural networks, all we are doing is we are going to the layer which is capturing the state of a certain cell on our board. We go find that layer, and we know that that layer is really based on the input from the layers below it. So we go and start adjusting the layers below it using a technique called gradient descent. Once again, I refer to that in my paper until we are able to flip the current state from white to black. So what did our model do when we flipped the E6 cell from a black disk to a white disk, as shown here? On the top of this diagram are all of the probabilities of the next move, which is before the intervention. And once we made this intervention, as you can see, the probabilities of the next move changed appropriately. So for example, the cell B3, which was not even in contention as a next possible move, came into contention because now a white disk has been placed in cell E6. So what this diagram is essentially telling you that our model was able to adjust to the intervention that we made artificially. So at this point, we have seen that the model can develop an internal representation of the board state. It has learned enough rules to deal with this intervention that we made, converting a black disk into a white disk. But you're asking yourself, sure, the model can now predict a legal move for the game Othello, but does it have enough understanding of the game to win the game? Does it develop a strategy for winning? Let's try to answer that question next. And I'm going to show you this diagram that is comprised of multiple tiles. So it looks a bit busy, but you've seen one of these tiles before. In fact, I'm just going to focus on one of the tiles. What we're going to do is we're going to run this model normally to get the next step probability predicted for a cell D6 that is highlighted with a black box there. Then we run the model again, but this time we're going to intervene and we're going to take the white disk on D4 and convert that into a black disk and run the model again. And what we are going to do is we are going to save the probability for both the runs. And then by taking the difference between the two probability values, we know how the current state of D4 is contributing towards the prediction of D6. So in this manner, as you can see, we are beginning to evolve a strategy. And the rest of the tiles, you can take the same behavior that I just talked about. In this manner, it is developing a strategy by flipping a disk, what is going to be the impact on the board state. I also want to point out a very interesting diagram from this paper. And once again, we see a number of tiles and the impact of interventions that we talked about in the previous slide. The top half of this slide represents interventions on a model that was trained on synthetic data. And the bottom half of this diagram shows you interventions that are based on a model that was trained on championship data. And it's very interesting to look at this diagram. So if you look at the interventions based on the synthetic data was trying to teach this model only to predict the next legal move. Remember, the synthetic data was generated by taking a game tree and generating permutations and combinations without regard to a winning strategy. But if you compare it to the interventions and the tiles in the bottom half of this diagram, you can see that it is more complex than the one on the top. Why is that? Because this model was trained on the championship data, and high caliber players, when they're making these moves, they're taking multiple factors into account, not just the next legal move. And this is why you see more complexity in the tiles that pertain to the model that was trained on championship data. So the thing to take away from this slide is our model not only learned the internal representation, not only developed a strategy, it also tried to understand, based on the championship moves, some advanced moves and strategies for winning. So with this slide, we come to the end of this video. Let's go back to the question that we posed at the beginning of this video. Are these language models learning a world representation based on the data that they were trained on? Or are they merely generating content based on surface level statistics? And I'll let you ponder on this question on your own. Whether you're convinced or not about the language models and what's happening inside them, I hope you'll agree that developing a better human understanding of this black box inside large language model is a step in the right direction and will continue to help us with the explainability of large language models. Thank you for watching this video.